Alright, hello class. This is CSE-5250, Section 2, Week 4. I know this video is coming out a bit late, but that's because of technical difficulties I had while trying to write up a Python version of the sieve of Eratosthenes. Hopefully I can show you what I tried to do and why or how it went wrong, but let's begin with a recap of what we're doing. So what we're doing right now is we're taking the program that we wrote in programming assignment 0. That was the sieve of Eratosthenes, and we're rewriting it so that it's a multi-threaded program instead. The idea is if we can make a parallel for loop in the code, we can divide up the work among multiple CPU cores and hopefully get some sort of speed up in the program. So let me show you what I had for you last week. First, let me show you something that I just found out recently that made me rethink everything I thought I knew about OpenMP. And let me tell you, it is quite a shocker. Alright, first off, there is a function. If you include omp.h and you go through the process of setting up Visual Studio so that it can accept. No, if you go through the process of setting up Visual Studio such that OpenMP support is set to yes, you have, and then you include omp.h, what you have access to is a function that can set the number of threads. Put this right before any parallel section of code. So this regular OMP parallel is defining everything within these curly brackets as a parallel section of code. So that will run on however many threads you have, or in this case, however many threads you set. Bearing in mind that my computer has 8 cores and 16 logical processors, I was always under the impression that it would always max out at however many processors I have. But nope, that's not the case. So we can set the thread count as high as we want. So, yeah. That's quite a bit of a revelation right there. Now, without any synchronization, what's going on here is each thread is printing out its thread numbers. So, with 256 threads, we have thread ADs of 0 to 255. And there's no synchronization between any of these threads at all. So I've just run this again and again and again. I will get all 256 thread numbers, in whatever order they just happen to appear in. So this is technically a random number generator, because there's no determinism to the order in which these threads. There's no determinism to the order of these threads. There's no synchronization at all. So any order that these numbers could appear in is basically up for grabs. 112, 177, 155, 245, 166, 122. So yeah, this is it's technically a random number generator now. Alright, so that's the revelation I wanted to show you. So let me just change up a few sections of code in here so we can see the sieve in action. Okay, so this is more or less the same exact sieve that we had last week, where I went through the process of writing the sieve and making a parallel for loop out of the innermost for loop right here. And really, that's all there is to it if you're going to use OpenMP and C++. What had happened was, I thought there was OpenMP support for Python. No, it was actually C++ and Fortran. Excuse me. So, if I set the number of threads to 1, I am basically back down to a single-threaded program, which is what we had initially. So, let's run it and see what kind of time we get. Okay, so we got an execution time of 2,793 milliseconds. And that's on one thread. Yeah, so just under 3 seconds to look for prime numbers up to 200,000. So, what if we added more threads? So I've set it to 2. 1,557 milliseconds, so the execution time got roughly cut in half. Let's add more. 1,020 milliseconds. So we're down to a second. Let's add more threads. 8. 658. So now we've reduced the execution time by about 25% of what it was when it was single threaded. Let's increase it again. 668. So not much of a significant difference here. Only going from 8 to 16 resulted in a very marginal decrease in execution time. Let's keep going. 32. Okay, now we're at the point where it actually went up in execution time. So this could be due to the overhead that's needed. This could be due to the overhead that's incurred by having the program be multi-threaded in the first place. So I do have another hypothesis. It's because I have 16 threads on my CPU, and because there's 32 threads in the program, some of the threads have to be queued up to wait for the CPU to become available. Let's keep going. 64, and it went up a little bit. Let's just go for broke and to 1024 threads. Yep, now it went up a lot. So yeah. Eventually, what I'm gonna have you do is to make a table of execution time. A table of execution times for varying thread counts and maximum numbers. So, you've seen that it took about 3 seconds to find prime numbers up to 200,000. Let's try a million. 1 million prime number. Prime numbers up to a million. And that is going to take us quite a while, actually. We can just wait for this to finish executing. 30 seconds to find prime numbers up to a million. Now, if I just increase that to 16 threads, what happens now? Six seconds. Okay, so eventually what I'll have you do is to make a table of execution times comparing thread counts and max numbers. What this maximum number here is changing how much proportion of the code can be made parallel. I've alluded to the idea of Amdahl's law, which is a formula that calculates the maximum speedup that you can get out of a parallel program given the proportion of the program that can be made parallel and the number of threads you have available. And the idea is pretty simple. 100% of the runtime will be taken by one portion of the program that cannot be made parallel. That has to be executed sequentially no matter what you do. And the rest is going to be whatever sections of code can be made parallel. So you have, let's call those X and Y. So X is the proportion of code that cannot be made parallel, and Y is the proportion of code that can be made parallel. So those two values add up to the total execution time. If X is very small, that means Y is very large. So even if you just have 2 threads, in the limit, what you have is a reduction of execution time by up to 50%. In the limit, of course. You could have a situation where there's barely any parallel programming that can be... You could have a situation where you barely have any parallel code, and any speedup that you would get is only marginal. So we can simulate that by having a maximum number of 100 and setting the thread count to 1. Here it took about 1 millisecond to execute the program, though I'm doubtful that this is actually 1 millisecond. The reason I'm doubtful is because this goes by milliseconds, and some of you may have your programs counting by microseconds. So it could be feasible that this program is executing in a few microseconds. So, oops. So it took about 1 millisecond to execute the program. So if I ramp up the number of threads to 16, what happens? 2 milliseconds. So it increases the execution time. But here's another thing to consider. If I'm looking for prime numbers up to 100, this results in a rather minuscule program. You would be looking at time differences where you're looking at such small time differences that you might conclude that it doesn't matter whether we make it parallel or not. But in larger cases, you're looking at situations where it does matter. So here with 200,000, here with a maximum number of 200,000, we're looking for prime numbers up to 200,000, and that simulates a program where there's a much larger proportion of parallel code. And what do I mean by that? In theory, we can unwrap this entire for loop into all of the in theory, we can unwrap this entire for loop. By that I mean, we can do something like this. So what we would have to do is assign current number to oh yeah, we also need a current prime. Yeah, in theory we can have this. So int current prime equals list number 0. Int current prime number equals list number 0. We can then just keep on copying this. What we can do is just keep copying the section of code, reassign current number to list numbers 1, x prime 1, 2, 2, and then we keep going all the way to 199,999. And then we repeat those 200,000 blocks of code with a current prime of list numbers 1, and then 2, and then all the way to the square root of the maximum number. So you can imagine the 2 for loops being unwrapped like that, and you'll realize that this is why we have for loops. But the idea is this awkwardly unwieldy code is basically a program with a very high proportion of parallelizable code. Because what happens is, well, here's the thing. To really drive the point home, I really should be doing this. And current number. What this does is make the code a little less readable. Hold on, I think I... Hold on. Alright. Yeah, I think I got it. What this does is make the code a lot less readable, but it makes it such that now we're in a position where we can scramble all of those blocks of code and it would still execute the same way as it did before. So the idea is to recognize a section of code that can be made parallel. If you have a section of code where you have several lines of code or blocks of code, where if you swap the order of execution, you get the same results, you can, in theory, have those blocks of code be executed at the same time. So, basically, what I'm trying to say is these blocks of code from the unwrapped for loops can be scrambled. They'll result in the same result. And therefore, we can parallelize that code by, well, having it back in the for loop, back in the form of a for loop. So, how about the benchmarks? Well, I can show an example of my own benchmarks. So this is what I did when I took the class for myself, and I'm more or less having you do some of the same things that I did. But later on, I'm gonna have you try a few more fun applications of parallel programming. We're just looking at a few ways of making parallel code. One thing to note here is how you can have a situation where if you make the code parallel, you make the performance worse. So check out this. Looking for primes up to 1000. With just one thread, I normalized the execution time to 100%, but if I increase the thread count to 16, the execution shoots up to 1100%. That's terrible. But at the same time, look at how minuscule these execution times are. We're talking about a few hundred to about 1,000 microseconds. That's very minuscule. Well, relative to the monster execution times we get for these, I was looking for primes up to 1 million and even 10 million. And here it took an entire second just to execute. So how come this took 1 second to execute, whereas the one I showed you took like 30 seconds? Well, the truth is, how I wrote this for loop was not well optimized. You see, in theory we could have it so that in theory we can have both for loops unwrapped. But the thing is, if you want a good speed up, what we have to do is add a check in the outer for loop, where if the current prime was already marked as non-zero, if the current prime was already marked as non-prime, we would skip that iteration of the for loop entirely. So really, by just scrambling the unwrapped for loops, we may have introduced a lot of redundant code. So really, a better version of what I just described, a better version of the unwrapped for loops is unwrapping the innermost. A better optimized version of the code would be unwrapping the innermost for loop, and then copying that for however many times we have to iterate the outer for loop. But we only scramble the contents of the inner for loops and not the outer for loops, if that makes sense. So yeah, there's various optimizations we could do before we even consider parallel code. But yeah, To what extent does this closely follows Amdahl's law? Well, Amdahl's law only accounts for optimal speedup. It doesn't account for overhead, which this line chart clearly shows. So, for nearly all of these, adding more threads does lead up to a increase in performance in that it reduces the execution time required for the program. Amdahl's law does not explain this blue line where we barely get any speed up and then it just shoots up and now we have nearly doubled the execution time. So, why is that? Well, in short, it's the overhead. There is overhead needed to fork and join the threads. These, when we have a multi-threaded program, it follows what's known as the fork and join model, and the super short version of what's going on is it takes time to fork and join the threads, and also there's no determinism as to how these threads arrive to the CPU. So, you'll eventually make a table similar to this, but it does not have to be as in-depth as how I did it. Really, I was just doing this for the sake of data collection. Really, this is the table. Really, down here, this is the table I want you to make eventually. It'll look more like the table will most likely look like this. So, yeah, but you can include other features such as this line graph. Alright, so next week we'll be looking at NVIDIA CUDA, hopefully, and I'll talk more about the benchmarks as well. But for those of you who are using C++ for assignment 1, you can basically just imitate the code that I have. You can also introduce more optimizations, such as the one I just talked about, where if is prime I not continue. So what is this? So I added that, and remember, this took about just under 3 seconds to execute. What is the difference if I added this small extra optimization here? Wow. Okay, so, but this is using 16 threads, so really I kind of screwed it up here. So, okay, so it really means that if you really wanted to test this optimized version of the sieve, we really need to ramp up the max number. 776 milliseconds, so that's nearly 1 second. So yeah, it really depends on how well optimized you made your sieves. But for those who are using C++, you can basically just add in this directive here. For those who are using Python or any other language, but you know how to make it parallel anyway, try it like that. But I will say right now, the next few assignments, the only option is C++. If you look back at the assignment, if you have any way of making a parallel multi-threaded sieve of Veritasities using anything other than C++ and OpenMP, and you know how to do it, and you know how to make it work, then definitely submit that. But the next few assignments will require C++. So if you do, if you are able to pull off making a multi-threaded sieve that doesn't use OpenMP or C++, and you can get a speed up, you can specify what you did by including a README file. So that's going to be it on the C++ section. I'm going to show you what I tried to do using Python. I'm going to try to explain my thought processes and what happened that didn't really make it work. Right, so here's a version of the sieve in Python. So if I run this, and this is in a Jupyter Notebooks, and in Visual Studio Code, it has this feature where it gives you an execution time, but down to a resolution of 1/10 of a second. So if you want something, 17.5 seconds. But I have it so that it starts counting right before the for loop and right after it, not before any of this. Just keep that in mind. But I'll just tell you right now that in the parallel attempts, I have it in the same position. So really, we're just timing how long it took for the nested for loop to run. So here it took about 17 seconds. About 17 seconds. And then we can do, as a sanity check, print out some of the prime numbers to make sure that, well, it did work. And it did. So here's the first attempt I did to make a parallel sieve of Eratosthenes. The first thing I did was I broke up the nested for loop, so the nested for loop is instead a helper function. But this helper function is set up a little bit differently. Let me explain. So the idea is, if you have multiple threads trying to access the same shared if you have multiple threads trying to share the same if you have multiple threads trying to access the same shared array, you cannot, if you want to have it parallel, you cannot have every thread access the same elements over and over again, because you're just basically doing the same thing as you did if it was single threaded, but now you're doing it 3 times over. No, multiple times over. So instead, what you need to do is set up the code so that one thread leapfrogs over one another, and we do that by introducing a few other things. So maybe I still have this up, but if not, here it is. So as a visualization, if we have 3 threads and they're all running the same helper function here, they have to start at different positions. So thread 1 has to start at position 1, thread 2 has to start at position 2, thread 3 at position 3. Ignore these values. They're actually not part of the lecture. They're actually part of a different class. So if you have 3 threads accessing the same shared array, you need to have them start looping at different positions. That's number 1. But that's easily done by realizing that each thread has its own unique thread ID, enumerated from 0, 1, and 2, so we can just use those thread IDs as their starting positions. Number 2 is, they need to leapfrog one over one another using a value known as a stride. And that number is easy to get too. That's the number of threads we have. So each thread is moving 3 positions to the next. And what happens is they leapfrog over one another. That's the best way I can describe it. And if you're to put it out in a pattern like... and well, this is basically the pattern that they form. It's like this diagonal stripes pattern. So yeah, that was the idea. The idea was... and that's only part of it. What's also part of what needs to happen is you need to have an array of threads. You need to loop... you have to iterate. You have to have a for loop that creates each thread, and then it has to it also has to be given the function that we're calling. It also has to be given the arguments separately in a tuple here. You have to also give it all the parameters. So start index, stride. In this for loop, the start index is the I in the for loop, and the stride is the thread count. So in this example where we have 3 threads leapfrogging over one another, in this example it's 16. We have to start each thread, we have to add them into the array so they don't get lost, and that is the part where the program forks into multiple threads. After that, we have to join them back with the main thread. So, we can try to run this program and see what happens. Execution time of 1.8 seconds. Is that right? Well, I haven't had another version here, so maybe I can just copy this and see if it was printing out, see if it did work. So let's run this again. And it worked. It executed in about 2 seconds. Probably because this is a .py. Maybe because this is a Python source code and not a Jupyter notebook. So that's another thing we have to consider. Right, I'll just comment that out. 2 seconds, and if I increase the thread count to 4, will this speed up? Yeah, we're not seeing any sort of speed up, and it's probably due to how Python works on the inside. I got surprised to realizing that there may be some intricacies as to how the Python interpreter works, and it might be disallowing threading altogether. So if there is a way to make a parallel sieve using Python, it has eluded me so far. But if anyone has a solution as to how to make it work anyway, you are welcome to do that as part of assignment 1. So this is another attempt that I did, and it shares a lot of similarities with OpenMP in that we don't have to do this start index and stride thing here. We just call this, and it should work. However, I had to add a few parameters to make sure that memory is being shared. In fact, let me just show you what happens otherwise. If I run this, it runs in 9 seconds. And if I had 4 cores, if I have it so it is 4 threads instead, it's still the same amount of time. So yeah. Maybe it's the fact that it's in a Jupyter notebook and not a .py file. But anyway, this is as far as I've been able to get with trying to make a parallel for loop using Python. And all I can say right now is that it has been eluding me. So if you know how to make it work in Python, definitely let me know via email or submit it as a submission for assignment 1. Programming assignment 1, which is the parallel multi-threaded sieve. This is going to be due on the 23rd. I know it's a little late, but I do realize it's a bit late with recording this video. So yeah. Next week we'll be looking at NVIDIA CUDA, and all I can say is that will definitely require C++. It will definitely require hardware that you may not have. Specifically, you're gonna need a NVIDIA graphics card. If you're like me and you build your own computers and you have in your computer NVIDIA graphics card, then you're basically set. You're basically in a position where you can basically do this kind of program at home without having to remotely access the Jack Brown Hall computers. If you have another way to access a computer with the necessary hardware, you're welcome to do that. You're welcome to do that as well. I heard you can rent server time and upload your program on to a server and execute your program that way. I don't know the specifics about that, but that is another route you can go. You could also just borrow someone's computer. But I'll explain a little more when we get to next week. Because of all the flooding on campus, we're a little bit behind. From what I've heard, it's pretty bad. When I went to the campus the past few days, there was like a disaster relief truck in the parking lot. That tells me it's bad enough. I've even seen footage of some of the buildings on campus being flooded. As in, there's basically a pool of water, and basically the floor was a mirror. Yeah, it was that bad. The last few times I was there, the student union building and the library and probably a few more buildings, they were basically out of commission. So hopefully that gets resolved sometime soon. It's a good thing that Jack Brown computers are on the 3rd floor of Jack Brown Hall. At least they'll never get flooded that way. But anyway, that's gonna be it for the video. Hopefully I'll get this uploaded as fast as possible. Maybe I can, what I did for a few past videos, I added chapters so you can, instead of just scrubbing through the video, hopefully getting, so instead of scrubbing through the video, you can just click on the relevant chapter and it'll just take you there. I'll try to do that with this video as I did with the last few videos. And that's going to be it for this week. Alright, thank you class. See you next week.